Okay, so hi all. Hope you're doing well. In this video, which I just recorded half an hour of which without any sound, so I will, thankfully I didn't get to the end of it before I realized that the microphone was not plugged in. So this will be a little bit of a replay for all of us. In this video, I'm going to mainly just do a one more example of Duhamel's principle, which is what we learned about in the last video, mostly just to show you, how bad it can get, I guess, right, is sort of the what we're all waiting for, I suppose, which isn't that bad. It's just a lot of stuff. So we'll get to that in just a second. I'll give you the very, very quick recap, especially since I just did this 2 minutes ago, of where we're at. So I think our goal this week is to figure out how to solve a non-homogeneous system of ODEs, which we've been very good and comfortable with this guy, or well, actually really this guy, which of course rewritten is just this guy down here. But that's actually, to match our lingo from ODE's class, that's more of a homogeneous system, because when you write it in the usual way we write an ODE, which is, y prime and y, all being on the left side, and then the stuff that doesn't have the y's usually is on the right, well, it's a zero. Oh, and we called that homogeneous way back when, so we still call it homogeneous here. But then we said that's nice, and we're all very good at doing those. But how about if we take the next step, which is to say, well, what if you have something over here on the right? A G of t, as we usually called it. Now, of course, the only thing different as it's been all week, or well, for the last few weeks really, with the system of ODEs, is that everything is 2D. So G of t is, of course, actually a vector G of t, which if we want to, we can think about that as having a top and a bottom, G1 of t and G2 of t, both of which are functions, whatever they might be, cosines and sines and e's and ln's and all of our usual friends might be over there. So how do I do this? Well, the good news is that especially when we kind of put these two next to each other, it hopefully reminds us that we had a wonderful way of doing this in ODE's class, where we, as long as we could find the two homogeneous solutions, and we were very good at doing that at this point, as long as we could find one non-homogeneous, which we usually maybe call a particular solution, or XP for shorthand, as long as I could find one non-homogeneous solution, then all the non-homogeneous solutions, or you could say the general solution, is given by, oops, that should have said and then, the general solution is given by if you take all combinations of the homogeneous guys, and then throw in your one particular non-homogeneous solution, that is a way of, or that represents all possible non-homogeneous solutions, which is great, right? That's all of them. So that if I can do this, I'm in good shape. All right, and what we learned about in the last video was that we have one strategy, and we're only going to really look at this one strategy for finding XP, this one particular non-homogeneous solution. All right, and we did a little proof, which I won't recap for you, but it's there, and we got a little bit of a preliminary result ready, because then we said, all right, so if I'm trying to figure out XP, one non-homogeneous solution, then let's do our favorite thing in ODEs, which is make a guess, use a helper, that's U of t is a helping function, and I'm going to guess that I get a non-homogeneous solution by taking this phi, which was which we called a fundamental matrix, which is essentially just your two homogeneous solutions written as a matrix. So it's just a shorthand way of us being able to sort of wrap together the two homogeneous solutions. So in some sense, this is us saying, take the homogeneous solutions, that's phi, and multiply by an unknown helper, and we'll hope that we could figure out who our unknown helper would be, or who it needs to be, in order to have this turn into a non-homogeneous solution. That's our goal. Okay, and of course U is really U1 in the top, U2 in the bottom, right? Because it's a vector. Okay, so actually we have two unknown helpers, right? U1 and U2, which are the two components of U. Okay, so if in a matter of time, if in a matter of a derivation step or two, we would be able to figure it out what U1 and U2 are, I'd be in good shape. So we did our usual thing, we plugged it in, and this actually wasn't that bad. This probably rates as easy on the algebra awfulness scale. That there wasn't a whole lot that needed to cancel for us to boil down to, I would say either start here at the top, or if you want the second line, is a good way of, is a good place to jump in and say, so, our mystery U's can be attained by starting, our mystery U's have to satisfy this fact, either the top line or written out more so it's this line, or I guess written out even more, it's this duo here of facts. And so now the only reason why I can't do a, hey, here's a cute formula that always gives you the answer thing, is because these aren't numbers. So x1, x2, the g's, right? These 6 things that are circled, those are functions, or they could be at least functions. Maybe they might just be numbers, but for the most part, they're probably functions. And so I think in terms of, the usual algebra stuff that we do, this is still a system of 2 equations and 2 unknowns, u1 prime and u2 prime. And so via algebra, you can still do a rearrangement, or maybe you do substitution, or maybe you do the one where you have two lines, 2 equations, and you draw a big line under it, and you say, I'm going to add them up now, or add a multiple of one to a multiple of the other. All those usual algebra 1 or algebra 2 maybe steps you could still do, and get it so that one of the variables drops out, one of the unknowns, that's u1 prime or u2 prime, one of them could drop out, and give you an equation for one of them that has just some t's in it. And then maybe you use that one to do a substitution into either of these to get an equation for the other one that only has t's in it. Aha! So you end up with being able to transform this, or this, wherever you want to jump in, into this, into, u1 prime equals, whatever, some stuff with t's, u2 prime equals whatever, some stuff with t's. Well, these are both easily solvable by saying, all right, if I integrate both sides, then of course on the left here I'll end up with u1, and on the left here I'll end up with u2. That's my goal. And then I just have 2 integrals to do in order to figure out who u1 and u2 actually are. They are helpers, so I don't need a plus c or any sort of constants here, because I'm just in search of one helper, not a whole bunch. Or I'm really in search of 2 helpers, right, u1 and u2. But so we did an easy one. This is non-homogeneous because you have something over here. But this was, well, I'll rate this as easy because of the idea that, of course, over here I just had a vector. So I didn't have to do a whole lot of work here. I mean, I did actually have to do a whole lot of work, but I didn't have anything too gross because I just had 2 and 4 over here. Now, of course, as you might imagine, if that was 2t squared and that was sine of t, I mean, your life is already getting to be a little more complicated, which we'll do one of those. But okay, but this worked out all right, and I was able to solve for u1 and u2. And then I'd say, I don't know, just to make sure you don't mess this up, I sometimes see people take u1 and u2 and then they put them back here and here. But remember, this is, first of all, that's u1 prime and that's u2 prime, so that would be wrong to do that. But also remind yourself, wait a minute, what was I using this u for in the first place? Oh, I was using this u as my helper to take phi times u, and that will now be my particular non-homogeneous solution. So at the very end of this problem, that's exactly what we did. We took phi times u, and multiplied, simplified, and we ended up with, actually, as it turns out, just a vector, 8 thirds, 10 thirds. Aha, okay, so here is our solution, right? The homogeneous piece plus 1, our one non-homogeneous solution, which in this case happens to just be numbers, right? 8 thirds in the top and 10 thirds in the bottom. Okay, now I didn't say this, but since I have an inch of space here at the bottom, let's ask and answer the usual question that we might be interested in at the end of one of these problems, which is something about, so tell me about what's happening with this thing. So let's do our usual thought, at least, which is what's happening as time goes to infinity with this. Does this blow up? Does this, where is this heading? Now, you could do a graph of this, and this one actually wouldn't be that bad to graph, because if I cover up the 8 thirds, 10 thirds for a second, so pretend that's not there, the homogeneous one, this is one we did last week, I guess it would have been. If I graph this, this is one where I have 2 real solutions, 2 real eigenvalues, -3 and -1. And in particular, we also, so these 2 eigenvectors, the flow is in towards the origin on both of those. So this would have been one where I would have said, oh, all the arrows are pointing in. When we do our phase plane, our phase portrait, we would have seen all the arrows pointing towards the origin, and I think this is something we would have called a sink, which is stable, because of course everything heads towards the origin. 0, 0, right? So so if I just graph the homogeneous piece, that's the same. That would be the same idea. Now, what does throwing this in have to do, or how does this change adding this vector? Well, remember, those are just points. So instead of flowing into the origin, which is what this piece, right, that's trying to head towards the origin. Here, let me start writing some of this down. So as time goes to infinity, of course, we know that e to the negative big is 0. So, of course, this piece is heading towards the origin, which I'll just write as 0, 0. That's where this piece is heading. Same thing for this piece, right? That piece is also heading towards the origin, 0, 0. But as t goes to infinity, where's this piece heading? Well, I mean, it's just itself, right? It's not doing anything. It's not heading anywhere in particular. It's actually just itself. So this is heading towards 8/3, 10/3. So of course, this whole thing is heading towards 8/3, 10/3. So while visually, I'm going to sort of just make up this is not going to be super duper accurate, but that's all right. If I was at least just thinking a little bit about a graph of this, I might say, well, okay, the homogeneous part is a sink, as we called it, right? So this is a sink. Don't write this down yet, but a sink that we drew in before just basically had all the arrows pointing towards the origin, right? In essence, that's what a sink does, is everything gets drawn to the origin. And in particular, as you go to infinity, as time goes to infinity, you're heading towards the origin. So whatever path you might be taking to get there, right, you're always heading in towards the origin. Well, so what's the difference between that and this one? Well, this is still doing that. The front piece here, this is still saying head to the origin, head to the origin. But this piece over here is saying, no, I'm not going to head towards the origin. I'm heading towards 8/3, 10/3. So a rough sketch, again, so now if you do want to draw this, go ahead, is to say, well, in the long run, I don't know where 8/3, 10/3 is, but I'll just pretend that it's there for a second. In the long run, while I'm being drawn in, that's what these guys are saying, these guys are vanishing. I'm being drawn in, but now instead of being drawn into the origin, I'm actually getting drawn into this point. So if I was just going for the ever so not super fancy sketch of what's happening in this problem, what's happening in this problem is that in the long run, all the solutions are heading towards that point, 8/3, 10/3. And if you wanted to, right, you could still draw your little vectors in, your eigenvectors. But of course, the eigenvectors are not solutions to the non-homogeneous problem. They are solutions to the homogeneous problem, but they're not solutions to the non-homogeneous. So actually, I think you have to shift your eigenvectors to have them, kind of go through 8/3, 10/3 kind of a thing, if you really wanted to draw those in. But let's not get too carried away with this, right? But for sure, right, the behavior of the graph is still dictated by, in this, the homogeneous portion, and by that I mean the arrows. But it has a new focal point, and in this case, since this turns out to just be a number, it's focused on that. All right, so it's kind of cute. We had this in front of us, so I wanted to take 5 minutes and at least just point that out. And that's probably somehow by design, right? The idea of adding this 2, 4 vector is adding some other component. Now notice, of course, 2, 4 does not turn out to be the solution, right? The non-homogeneous solution is not 2, 4, and 2, 4 is not the sink either. It's actually 8/3, 10/3, right? So there's other dynamics happening in the system aside from just those numbers specifically. But yes, that is, of course, those two numbers are what lead us to being able to compute or figure out what the new sinking point is, or attraction point, or whatever you want to call that. Okay, enough of that. On to what I mostly wanted to do in this video, which was to do a harder problem so you can see the, or I guess some of the ugliness that you might be dealing with. So that's example 1. So let's call this example 2. And I'm going to cheat a little bit here and use the same homogeneous part so that I don't have to do a big resolve thing here. So I'm just going to use the same homogeneous piece. And now I'm going to throw in a more complicated G. So now my G, it has T's in it, right? Okay, I think in the book, or I should say on WebAssign, when you see these, sometimes they write them with a matrix like this, and other times they just give you the top equation and the bottom equation. So don't be freaked out if you're like, oh my gosh, this doesn't look exactly like it. Just rewrite it in matrix format, which shouldn't take you more than 15 seconds, and then it'll look like this. All right, and just separate the part out that has the x's versus the part that doesn't have the x's. The part that doesn't have the x's, that's your G of t. Okay, so here's our problem. So I'm just going to, this is the same one. So this is the same homogeneous solution as the last one. So I'm not going to repeat all of that stuff. Let's just cut to the chase. In the last one, we came up with an eigen value of -3 and -1. And the eigenvectors were -1 and -3 and -1. And the eigenvector, let me just write this down. So we got lambda equals -3, and that has an eigenvector of -1, 1. And we had an eigenvalue of -1, which had an eigenvector of 1, 1. Okay, so of course from there, the two homogeneous solutions, x1 and x2, are of course k e to the lambda t. So k e to the lambda t and k e to the lambda t were our two solutions. Okay, so that's the homogeneous piece done, or redone, I guess. And so now we say, all right, I need the non-homogeneous, particular non-homogeneous solution. So again, we're going to guess that we get a particular solution by taking our fundamental matrix times our mystery U. That's our guess. Oop, and guess has just two S's. Okay, so in order to get this rolling, I should probably write down phi and what I'm trying to solve for and all of that good stuff, right? So here's where I might just jump a little bit and say, well, so what is it? I'm not going to you don't rederive this every time because you're going to waste 5 minutes of, oh yeah, okay, move this and blah, blah, blah. Okay, so we know, right, that in order to compute, so to find the correct U helper, we need to solve that phi, here, I'll write it here. We need to solve that phi times U prime equals G. Let's cover your G. Okay, that's what we're trying to, so that's what we're about to write down in expanded format, right? That's what the substitution boiled down to. Okay, so I need to do phi. Now phi are my two solutions written as columns. So of course my first solution is -1, 1, and then times e to the -3t. So of course that would be negative e to the -3t and e to the -3t, if I wrote that as a column. The second one would be e to the -t in the top and e to the -t in the bottom. Right? That's how that would break down. So that's my phi. Times U prime, so those are my mysteries for now. So I'll just leave them as such. Don't know the top, sorry. And don't know the bottom. And then G is, of course, this. Okay, so I got to do my algebra, or the linear algebra first, followed by an algebra step here. So if I multiply, let's see, so if I do row times column, I get, let's see, what do I end up with? Negative e to the -3t, u1 prime, plus e to the -t, u2 prime. And that's supposed to equal 2e to the -t. So that's my top row. My bottom row says take this second row and multiply, so I get e to the -3t u1 prime plus e to the negative t u2 prime, and apparently that's supposed to equal 3t. Oh, did I do 3t? Oh, I'm sorry. Sorry for a second here, although you're going to thank me later. That was the problem I started doing, and it turned into something completely terrible. So sorry about that. If you would do us all a favor, switch that bottom to e to the t. Sorry about that. It works. The other one works. You got to do integration by parts, and I mean nobody really wants to do that. So sorry. So switch that to e to the t, e to the t, e to the t. Okay. So let's see. So my goal at this point is to always be able to say, or to take these two and say, all right, I gotta do some algebra in order to get to the point where I have something that might say u1 prime equals some stuff with t's, or u2 prime equals some stuff with t's, and if I can get that far, the rest will sort of fall out. Now, just like we saw in the example when we did this a minute ago, I think if I just add these two equations, we might notice, of course, that the u1 prime piece is going to cancel. Now again, you might say, well, he's doing the ones that are easy. What if it doesn't just naturally cancel? Well, the worst thing that's going to happen, I mean, it should either automatically cancel or is at least going to be pretty darn close to canceling. I mean, if this had been a 2, then I would have had a 2 here. Oh my gosh, how hard is this to do? Not hard. Double the bottom one, and then you have a 2 here. And then when you add, the same good thing happens, right? So, I mean, as much as I know these are a little less pleasant to look at than if you just had numbers everywhere, all the same tricks, let me get rid of that too, all the same tricks still work. All right, so be brave here, right? This isn't as bad as it probably looks in most cases. All right, so if I add, let's see, so if I add vertically, of course, that's 0. And then here I get 2 of them. Again, you're going to have nice things like that because all I'm doing is I'm adding the vector, right? So, I mean, these are both going to be numbers. I mean, you're never going to have anything worse than just a number in front of this. So, okay, and then over here I get some stuff. Unfortunately, I can't put those together. So I'm just going to leave them as is. Okay, but this isn't bad because now with just a simple division, I end up with u2 prime equals. And if I divide 2e to the negative t over to the right-hand side, well, that's actually the same as this first piece, so I'm just going to get 1. And now on the other piece, let's see, what do I have? A half, and then e to the 2t. Okay, now you could either finish this one, which is I think what I'm going to do. In other words, I'm going to solve for u2 and figure out how much it is. Or you could go back, you could say, okay, hold or pause on that. Let me get a u1 prime looking nice. Actually, maybe I will do that just so that I can then transfer these both to a clean slide. But if you want to finish this and say, okay, now let me integrate and figure out what u2 is, that's fine. But I'm going to save that for the next page. So I'm going to carry that one onto the next slide here. But before I leave, I'm going to say one more thing, which is that I'm halfway there, but I also want an equation that says u1 prime equals some stuff with t's. So for that, I'm just going to go back to either equation. Maybe I'll take the second one. And I'm going to take this as a substitution for, in this case, u2 prime. And we can hopefully see that if I put u2 prime, if I plug in what that is, or what I just discovered that is, I should be able to get a reasonable equation. So e to the negative t, and instead of u2 prime, let me fill this in. 1 plus 1/2 e to the 2t, and that's got to equal e to the t. So I just took the second equation, and I dropped that thing, in for u2 prime. Now, this looks a little messy, but I think I'm going to be able to rewrite this as u1 prime equals stuff with t's. So let me distribute this first. Or actually, maybe I'll clear this out. So if I multiply by e to the 3t everywhere, that'll clear out this, or you could say you're dividing by e to the negative 3t. So I'd end up with u1 prime. Here, let's see, if I multiply by e to the 3t, I get e to the 2t. And over here, I'd have e to the 4t. All right, so that's me just making the algebra look a little cleaner. And now I just need to move these guys to the right-hand side. So u1 prime, maybe I'll multiply it out first. So let's see, I have e to the 2t and 1/2 e to the 4t equals e to the 4t. Oh, sorry, so u1 prime, if I move these guys to the right side, u1 prime equals, so let's see, of course, when I move 1/2 of them to the other side, I'm going to subtract 1/2, which leaves me with 1/2, and then minus e to the 2t. Alright, so I end up with, not a bad, I'm not done, of course, but I get two equations, one equation for u1 prime and one equation for u2 prime, but they both just have t's in them, which means they're both in perfect shape to be integrated in order to be able to find u1 and u2. All right, so let's do that so we can get them. So carrying these over. So to solve now, it doesn't matter what order we do them in. I guess I'll do 1 before 2. So u1 prime, as it turns out, was what? 1/2 e to the 4t minus e to the e to the 2t. Is that right? Yeah, okay. So now, of course, if I integrate, I get u1 is, I just need to do these. These are both easy. These are easy integrals. So I think I'd end up with 1/8 e to the 4t and 1/2 e to the 2t. Okay, so that's my mystery u1. I had u2 prime was 1 plus 1/2 e to the 2t, I think. Just double check. Yes, 1 plus 1/2 e to the 2t, yep, okay. And so now I'm going to integrate both sides of that. And so that'll say u2 is, so t, and then this guy is, 1/4 e to the 2t. Okay, so this is our mystery u. So that's our u. I'll put an exclamation point to indicate not factorial but happiness, right? So that's our mystery u, has that stuff in the top and that stuff in the bottom. Okay, so we're at least done with the calculus piece. We do have a little bit of an algebra piece left, which is to say, all right, so that's my mystery u. So what was I going to use that for again? Oh, that's right. Phi times u is my solution that I will have sort of engineered at this point now to work. So I got to do that step. So that's my mystery u. So our particular non-homogeneous solution is phi times mystery, not mystery anymore, discovered u. So let's write down what that is. So phi, I got to bust out the matrix one more time. So 3t and e to the negative 3t and e to the negative t and e to the negative t. And now times u is that stuff. So, okay, 1/8 e to the 4t and 1/2 e to the 2t and t and 1/4 e to the 2t. Okay, that's my u. And I do have to multiply this out because, well, I shouldn't say of course, but what's going to happen is you're going to get some simplification and cancellation here, which we do want to do in order to sort of neaten up our answer in the best possible way here. So I'm going to multiply here. So just the usual business, row times, now this is just one enormous column, right? This is just a vector. So row times column, I'm going to end up with some stuff and some stuff. So let's see. So I'm going to multiply and distribute at the same time so that I don't have to write this down 17 times. So I'm doing, of course, e to the negative 3t times those guys, and e to the negative t times those guys down below. So if I do negative e to the negative 3t, I get negative 1/8 e to the t. And then minus and minus equals plus, so plus 1/2 e to the negative t. So that's negative e to the negative 3t times the top, and now I'm going to do e to the negative t times the bottom. So that's t e to the negative t, and 1/4 e to the t. Negative with 2t. All right, so that's a mouthful. But you can already see that there's at least a little bit of stuff I can put together up there. Okay, now I got to do the bottom. The good news is the bottom is actually the same as the top, just that this had a negative and this doesn't. So basically I could cheat a little bit here and just recopy those first two, but switching the signs. And then the second piece is identical, so I'm not even going to think. Okay, now that's of course just, in this example, that won't always be true, because you might have, it's because I had a 1 and a 1 as my vector, right? But obviously if that's not true, you're going to have to multiply them out. All right, well, I did this so that we could do a little bit of rewriting. So allegedly that's a thing that I can simplify ever so slightly, and not a whole lot, to be honest, but I guess I could do a little bit of gathering here. Actually, I'm just going to go to a clean slide. But as you can probably see, right, those guys could go together, and similarly those guys can go together. That's about it, I think, at least in terms of combining stuff. So I'll do that. I'm just going to another slide here. So again, this was all for us to be able to figure out xp. So if I combine those things, I think I end up with an eighth e to the t and 1/2 e to the negative t and t e to the negative t. I'm just copying off of my paper, but let me make sure I didn't. So I put these two guys together, that guy and that one. That's 1/8 e to the t, and then I think I just copied those down. 1/2 e to the negative t and t to the, yeah, okay, good. All right, and then similarly in the bottom, I think I end up with 3/8 e to the t minus 1/2 e to the negative t, and then that piece is the same. All right, so a little bit of simplifying gets us there. And that's all right. Now I'm just going to say, the cool kids, though, are going to do the following to this. And by cool kids, I mean you all, because I think the book, WebAssign, I think is making you put your answers in a sort of cleaned up format here. So once we get to this, okay, this is fine. But maybe this isn't too crazy to say, does this not just sort of look like, I mean, you have the same thing here, here, and here. Oops. Jeez. Here, here, and here, right? So cool kids would say, oh, well, that's really actually just the vector 1/8, 3/8 times e to the t. And then this is the vector 1/2, negative 1/2 times the scalar e to the negative t. And then this last one is the vector 1/1 times the scalar t e to the negative t. Right? I'm not doing anything too fancy here. I'm just collecting together like things. It's sort of the equivalent of, I don't know, it's just factoring out, I guess, or something like that. I don't know what you want to call that, but that, whatever that is, that's not hard, right? We could all do that. Now, the reason that we might do that is a little bit, just for style, I guess, and to maybe be able to summarize. It's shorter, right? It's shorter to write our answer. But then if you hearken back to the original, to the homogeneous, you see a little bit maybe, or you maybe see some things here. The eigenvectors here, right? 1/1 and -1, yeah, and opposite signs. I mean, the eigenvector 1/1 is here. This is an equivalent, at least, of the vector 1, -1, or -1/1, right? Same thing in the top and the bottom. And then this guy's sort of the odd duck. I guess I shouldn't say odd duck, but that's those eighths didn't appear anywhere earlier. So it's a little bit to sort of give a shout out to the fact that you're going to have vectors that are related to the original eigenvectors. But it's also so that when we write down our answer, we can maybe see if there's some absorption. So let's do that. All right, so first of all, here's my non-homogeneous particular solution. So at long last, our general solution is, so C1 times our homogeneous solution, which by now I think I should probably have memorized, and yet somehow I don't. Okay, it's -1/1 e to the -3t, and 1/1 e to the negative t. That was our homogeneous solution. And then plus our one non-homogeneous, which is this stuff up here. So maybe, hopefully, if I'm trying to be a good salesman here, that it's going to make the non-homogeneous at least kind of look like the homogeneous a little bit. So rewriting it is sort of cute, I guess. But now, finish writing that down. Yeah, okay, that's a mouthful for sure. But now's where somebody, if we were in class, I would say, now somebody tell me what's silly. Or I would ask, is there something silly that I could do in order to rewrite or do some absorbing? So if we remember, of course, way back when, we saw in ODE's class that sometimes when you get a non-homogeneous solution, that's that guy, parts of it can be absorbed into the homogeneous solution. And by absorbed into, I mean that it's redundant. You don't need to both say on the one hand, because what is this saying? This is saying take any number of those and any number of those. Right? That's what C1 and C2 mean. So if I was to have something out here, which could be encompassed by, or swallowed up by, or covered by those first two guys, the homogeneous pieces, I would want to sort of strike them and say, oh, you know what, I don't also need this, because I can just, it's already covered. Okay, so here's where I would dramatically pause in class and stare at you for 20 seconds before someone put their hand up and hazarded a guess. Can I suck any of these three pieces in the non-homogeneous? Could any of these be absorbed into these guys? And I'll help us out by at least saying, well, there's no way that the last guy can. That's t e to the negative t. Well, I don't have that. Okay, so you're in. You're good. E to the t, I don't have that here either. So this guy's good too. The only candidate would be the middle term here, because this is e to the negative t, and this is e to the negative t. So the question is, can I take that and just say, you know what, swallow that, or absorb that into that? And I would probably take a poll and ask you who says yes and who says no, and I'll go ahead and assert that some of you maybe would be in each camp, some yeses, maybe some nos. So what do we think? Well, if the answer is yes, then I would have to be able to say, by choosing an appropriate C, in this case C2, you'd have, all of this represented. In other words, whatever, this is an actual thing, right? This is 1/2 in the top, negative 1/2 in the bottom, and both of them are multiplied by e to the negative t, right? That's that's a single thing, a real thing. So I'd have to be able to say that's covered by this. So dramatic pause over, and answer is no, you can't absorb that in, because what do all of these guys look like? So what do they have in common? Obviously, yes, right? They both have a scalar of e to the negative t. But look at what's up front. This one is a vector where the top and bottom components are equal. Right? Whatever I pick for C2 is going to end up in the top and the bottom. So that this is a vector like 6, 6, or 11, 11, or negative 2, negative 2. Well, that's not this. This is the vector 1/2, negative 1/2. So since I can't make this by a clever choice of this, you can't say that it's redundant. In other words, it is necessary to leave that there. Now, of course, if this had turned out to be, let me clean this up a little bit. If this had turned out to be 1/2, 1/2, 1/2, then absolutely, this would be redundant. And I would just cross it out and say, nope, I'm not even going to include that, because you don't need to also say, throw in any number of these, and then throw in an extra half of each, so to speak. That'd be silly. Just do less when you did this in the first place. Okay, so if that was true, I would cross that out and just write the other 4 terms. But since it isn't, I am going to say that's my answer. Which requires our biggest box ever, I think, in order to circle. Okay, so that's our. Okay, I mean, maybe it's not the best, it's not the worst. It's it is what it is, I guess. The good thing is that we can still have a little chat. Now this one's a little harder because, of course, the homogeneous. So in talking about graphs or what's happening in the long run and stuff like that, I can certainly still answer this question. This isn't going to be hard. Oh, I'm sorry, I was putting an n under there, wasn't I, earlier? So our non-homogeneous general solution. So as t goes to infinity, I can still pretty easily answer the question: where are all of these characters heading? This one's heading towards the origin because I have a negative. This one's still heading towards the origin because it's negative. This one's heading towards the origin because it's negative. This one, I have a little bit of a tug of war here, but I don't want to bust out too many fancy calculus things, but L'Hopital's rule, you could use that here. E to the t is a much more powerful force than just t. So t, this is really t over e to the t. E to the t pulls much harder than t. So that wins the tug of war, and this will also be going to 0. So third term is heading to 0. Last term is heading to the origin as well. Oh, okay, but this piece, oops, I skipped the wrong one. Sorry. Fourth and fifth pieces are heading to 0. 0, 0, 0, 0, 0, 0. But middle piece there, the third piece, this guy, of course, as t gets big, that's getting big. And the fact that I'm multiplying by an eighth and 3/8 doesn't really make a difference. This is heading towards infinity and infinity. Okay, so I'm pretty sure this whole thing is, of course, then heading to infinity, which some of the cool kids might write that as the infinity vector to say infinity in both components. And if you could even throw a plus or minus. I mean, these are both positive, but even if you had one of these was minus, if you want to just do a plus or minus, you can cover yourself. We never really care that much about plus infinity versus minus infinity. Big is big, so, and usually is bad. But so for sure, as time goes on, this thing's blowing up, right? So this is heading towards infinity. Graphically, this is a tricky. I wouldn't even attempt this because this is our same sink. This is the sink that we had. All the arrows pointing towards the origin. These guys are heading towards the origin, but these guys are racing towards infinity, and they're doing so along this vector. So, well, I mean. The vector 1/8, 3/8, so 1/8, 3/8 is, I don't know, maybe that. Whatever. So in the long run, everything vanishes except this piece. And what happens to this piece? Well, it's being shot out towards infinity. So the solutions, whatever it is that they might be doing and being attracted to the origin and all of that stuff, are eventually just riding along that vector. Also in the other way, too, if you really wanted to. Right, so of course in the long run, I'm heading towards infinity. I actually happen to be heading towards infinity along this, we could call this asymptote, 1/3, 3/8, 1/8, 3/8 vector. But the point being, right, in the long run, this is heading towards infinity. And from every direction, or in other words, no matter where I start, there's no way for me to avoid going to infinity. Okay, so of course this would be unstable because I'm heading towards infinity in all cases from any initial point. Okay, so, right. So, I'll leave myself here at the end, I guess. What I guess I'll say what can go wrong, I suppose, obviously, when we're doing these. Well, I mean, come on. Obviously, the answer is algebra and probably not so much calculus because they're not doing very much of it here, although there are some integrals to do. But mostly, sure, right? I mean, this is like algebra landmine city of lots and lots and lots and lots of algebra. So, as usual, I'll say deep breath, take your time. Probably end up in most cases with something that's bonkers at the end if you have an algebra issue. Obviously, if you're doing the homework problems, you can check them to see if they're right. Mostly just be careful of algebra kinds of things and just copy down mistakes sometimes even and all those sorts of things. and just do the best you can. Obviously, it's I won't show you my version of me doing this problem, but I promise I have a couple of crossouts of oh gosh, I forgot this, or oh gosh, I multiplied these things wrong, or who knows what. So so good luck with these, though. There isn't much. I don't have anything more to tell you or show you. So this is I think a little bit of a shorter video, but this is the end of our of the chapter on systems of ODEs and solving systems. So you know everything that I do at this point on solving systems. This is also going to be the end of we should be having a toast or something. This is the end of the ODEs portion of our course, and we will, after the exam next week, switch over to PDEs, which of course is originally at least what this class was called. It's since been sort of remodeled as a differential equations part 2, since it's a mixture of ODEs and PDEs. But I guess I should say fear not, or fearful, if that's the right way to say it. Solving PDEs oftentimes just involves solving ODEs, so it's not as though we're going to be divorcing ourselves from a lot of these kinds of ideas and strategies and make a guess and plug it in, and okay, this is still how we're going to kind of work through PDEs, but the PDE will let us explore a whole nother world of kinds of functions and solutions and real-life scenarios and all that good stuff, which I think is pretty neat. But PDEs are very hard, so it's kind of good that we have, whatever, our 5 weeks or so left. It's sort of just about the right amount of time for us to do stuff without it getting, like, batshit crazy and I can't solve any of these anymore kinds of things. So a couple last comments, I guess. So you're all set for the homework, so check it out. It's in WebAssign. And it's all of these. It's using Duhamel's principle to come up with a non-homogeneous. I think for most of them, they're having you present the general solution at the end. So in other words, what's in the box on the screen right now. I believe they're sort of, I think they force you to kind of rewrite it this way, with the vector notation kind of thing. I guess you could try it the other way, but I think at least the way that all the solutions are written in the solution guide thing, they're all written like this, where they pull the scale, they pull the function piece out, and then just have numerical vectors to type in. So, which is, to be honest, like I said, is the better way to do it anyway. So, so good luck with those. I'll be in contact probably over the weekend-ish with some details about the exam next week. Obviously, there's the usual questions to be answered about that, but then the not usual questions to be answered, which is, of course, the I'm here and you're all wherever you are, and so how are we logistically doing it? But it won't be. I don't think it'll be very different. I gave an ODEs exam today, actually, and aside from some panicky, I don't know how to upload these things moments, I think it went pretty smoothly. So I will give you largely the same story over the weekend. We are going to do it semi-synchronously, in the sense that you're all going to be doing it at roughly the same time, and that time is going to be on Thursday. We'll use our class period time, so Thursday up next week. Oh gosh, I'm bad with the dates. 16th, maybe? At our usual 11 a.m. Time slot, with some modifications. So try not to resist the urge to send me an email before I give you the whole speech about how this is going to work. But I will do that this weekend, so that you know what to do. And of course, usual things, review problems will be appearing at some point as well. Yeah. So, all right, at this point, I'm just talking. So good luck with the homework. As usual, if you have questions, let me know, and or pop into some Zoom office hours with me. Send me an email ahead of time, though, if you're interested in doing that. And I will be in touch over the weekend.